My name is Anders, as you can see here. I'm here to talk to you about Docker. Anyone using Docker right now? Oh, quite a few. Yeah, let's start. First, a little bit of information about me. I'm a programmer since about 20 years. I work at a consultant company called jDays, which has offices in Malmö and Copenhagen, San Francisco, and Stockholm. I consider myself a full-stack developer, and that means I enjoy web programming, UX programming, but I also enjoy writing SQL and whatever else there is in programming, I think. So, here's a quick overview about Docker, or about this talk, actually. So, first I'll just talk about what Docker is. Then I'll go over to why you should use Docker. And then finally, we'll go into a deep dive into how you're using Docker, and most specifically, the CLI. So, what is Docker? One thing you can see is it's like a lightweight virtual machine. But the difference between a virtual machine and Docker is, you can see it in this slide here. Instead of having the hypervisor and an extra guest operating system as you have in a virtual machine, the Docker engine is running right on the host. And what this means is that it is running as a process. Every Docker process is running as a process on the host. And you can see this if you run a process tree. So if to the left here we have a virtual machine running, virtual box. And there's a bunch of processes, the same processes running in both Docker and the virtual machine. And on the virtual machine, you can only see the virtual machine process on the host. But when you do the same thing on the Docker machine, you can see all the processes, because these processes are actually running on the machine. So they're not virtualized at all. Another difference is between the size of the machine. So a virtual machine is often fairly large. It can be like 2 gigabytes commonly. And a small-sized Docker container is 0 bytes. That's the scratch container. But if you have something that just has a binary in it, it may be something like 5 megabytes. That's a common use case. The startup time is a lot quicker too. A Docker container starts up in less than a second, while it usually takes about 1 or 2 minutes to start up a virtual machine. And then the networking integration with a virtual machine. If you try to set up a few virtual machines on your host and try to integrate them in a sensible way, it's very painful. But Docker is set up with networking thought of from the beginning. But that doesn't mean that we'll stop using virtual machines, because since most of us are running everything in the cloud right now or on virtual machines already. So the typical setup will be something like this. So you have a virtual machine where you're running a guest operating system, and then you're running Docker on top of that. But the good thing about this is, okay, this works fine and you can virtualize everything, but if you really need the performance, it's easy to just strip the virtual machine away and then run Docker on hardware instead. And a different way of seeing Docker is like change root on steroids. And change root is like a jail where you say that everything between inside this dashed box here, it's only accessible to this process. But Docker is more than just locking files. It also locks up networking and other stuff. So why do we want to use Docker? The main reason is better utilization. A long time ago, like in the late 1900s, we used machines, real machines. And then if we had one application running on the machine, then we had to buy an entire server, and then maybe we don't get any traffic. So we're wasting the price for an entire server. Then in the early 2000s, virtualization became a big thing. And it got a little better. But it was still the same problem. If you have a virtual machine, it reserves a lot of memory, and you don't get full utilization for the machine unless you really have a lot of customers all the time. But if you're using Docker, then you can split it up and have a bunch of applications running instead of having a bunch of virtual machines. And that allows you to have better utilization. Another reason for using Docker, this is actually the same reason why we're using virtual machines, because we can isolate everything and have it running without anything else interfering on it. And this is what Docker calls the matrix of hell, where you have a bunch of different applications or services, and you also have a bunch of different machines where you want to run this. So you have a development machine, you have a test machine, and you have a production machine, you may have a staging machine, and you need to set everything up. And everything is kind of the same, but it's still different. And it's painful to configure everything to work. And the Docker solutions to this is to just, okay, Docker is the unit of abstraction. This is what we're using everywhere. So you can run on your development machine the same container or the same image as you can run in production. It's very nice. Docker is also the contract. It becomes the contract because it's often operations that handle the hardware or the virtual machines. And what Docker is, it says, okay, the operations are expecting a container, and it will give it this environment, and it will give it these ports open. And as a developer, that's what you need to program for. So, as a developer, I know for sure that I'm one of these developers. I always want to use the newest things, new environments. I want to use Go, I want to use Node.js. There's a lot of changes all the time. But one thing I do like is isolated dependencies. And with operations, it's totally different. They want standardized environments, they want few changes, and they want to make the changes when they are ready to make the changes, which is sensible if you're into operations. But they also like isolated dependencies, and that's where Docker comes in. So it puts the love back between developers and operations. And the cool thing about Docker containers is that they can be pre-configured, and so operations may be really good at optimizing, say, an Oracle database. So they can do that. They can prepare the container, and then we can just use this container on our laptops, the same container that we will use in production. So the speed is also really important, because if it takes 2 minutes to start up a virtual machine, you will probably not do it as often as you should. But if it takes a second, it's not a problem. So being 100 times faster enables a lot of things. It enables you to set up throwaway development environments. You could set up databases, file system, and just have them in a container. You spin up the container, it takes 1 second, and then you can do a lot of changes to it, mutation testing, a lot of stuff, and then you just throw it away and start it up again, and it's clean. Really cool. And that's the same for throwaway test environments. Production environments, in that case, it's, say, if you want to upgrade your server, you want to use Nginx 1.9 instead of 1.6 or whatever you have, then you could just have 2 versions installed on the same, because it's just a new container that you spin up on the same production environment. And then you can just swap out the caches, and they can reuse the same preloaded caches. So, Docker in depth. Docker is a client-server solution. So you have a Docker client, which is commonly the CLI, but it can also be a web client or something different. And most of the time, the Docker client, if you're running on Linux, then it is running on the same machine as the Docker host. So the CLI talks to the Docker daemon via a TCP socket, or usually a Unix domain socket. But you can also set up the daemon to listen to TCP, and then you can just have a Docker client running on a different machine talking to your daemon, which starts up a lot of containers on the Docker host where the daemon is running. And if you're using a Mac or Windows, that's actually how it works. You run a virtual machine, usually VirtualBox, on the host, and that runs the daemon. And then the CLI you're running in your own operating system. So you're running the CLI on Windows, or you're running CLI on Mac OS. And then it talks to the virtual machine over TCP/IP. So some Docker concepts. We have images, which is like snapshots of a file system. We have containers, which is running images. So it's a process running that is based on an image. We have a Docker file. The Docker file is like a recipe for creating images, and also for how setting default values for starting containers. And then you have volumes, and volumes is something that's actually not inside Docker. It means that some files you don't want Docker to handle because you don't want them to be reset when you create or start a new container. So you have a volume that's mounted into the container, but it's actually running on your host. And images are also stored in a registry. So you have a common registry where you can download the images from. And the most common one used is it's called Docker Hub, but you can also set up your own image registries. So interactions between these things. So you build an image from a Docker file. You can tag an image so it's easy to find it. You can push it up to a registry, or you can pull it from a registry. When you run or create from an image, then you start or create a container. A container can be stopped, started, and restarted just like a process. And if you have a container that has been running for a while, you can commit it, and that will create a new snapshot of the files that are in the container. And the volumes, I'll get more into volumes later. So, images. Images are just a hierarchy of files. But there's some additional metadata that will be used as default values when you start up the container. And images are built from a layered file system. So in this example, we have the Linux kernel in the bottom. Then we have a couple of images, a Debian image, that's just one layer, a BusyBox image that has also just one layer. But when you start the BusyBox container, a new layer is created. So everything that happens in the process will be written to this top layer. And if you delete files from the lower layer, it's actually not deleted. It's just tagged or marked as it is if it was deleted. So if you start up a new BusyBox container, it will still contain all the files. And whenever you do changes from a Docker file, a new layer is created. And then whenever the container is started, all these images are merged, so it appears to the process as if they are just one layer. Yeah, I think you can read it. There are a few commands for listing images and creating images, but I won't go into all of them. I'll just select a few of them. So here's a container where you can run a command to get a listing of containers. And the containers you can see here, I don't know if you can read it. The top one, the root element there, is called scratch. That's the image that all other images are created from. That's the 0 file image. It has size 0. And then there are all the light blue ones are tagged images, so they can be addressed by a name. But all the other ones are they just have a hash, like a git commit. And as you can see, some of them are created from the same roots, and some are not. Here are some example sizes. Like I said, the scratch size is 0. BusyBox is 2.4 megabytes, but it contains 10,500 files. And the reason that this works out is that it's mostly just links into to the same binary that handles everything. If you go up to Debian, it's about 122 megabytes. Debian is often used as a base image for other images. And then the Ubuntu image is 188 megabytes. So to create images, we have 3 commands. You can have a running container, and you can commit it. Then a new snapshot is created. Or you can import. You can just have a tar file or a URL to a tar file, and then you do Docker import, and then a new image is created. But the most common way is to use Docker build. And the reason for that is that if you're using Docker commit, so here's an example session where I run a few commands, apt-get update, apt-get install Postgres, and then I try to install Node, but it doesn't really work, so I change my mind and install IO.js instead. And then the final thing I do after exiting is that I commit this image, and I call it Postgres IO.js. And the problem with this is that, okay, everything I did there when I tried to install Node, that didn't work. It may have added files and or done some strange things, so I don't have full control over my image. So if I instead use a Docker file, I would just write it down like this. So I base it on Debian Jessie, and then I use the run command inside the Docker file, and it will do all the things that I did at the CLI before. And then I just Docker build and tag it. And one thing about this is that every one of the run commands will create a new layer. So there will actually be like 5 layers here, and most of them will not even have a name, and I don't really care about them. So if I don't care about them, I can do it like this. I can just do one run command and then just group all the commands together like this. And then it will only create one extra layer for all these commands. And there are reasons for doing both. If you're going into production, it will only have to make one request for the layer when you pull it down from Docker Hub. So it's nice to have the production images as flat as possible. But when doing development, images are cached by their commands. So if you have a lot of stuff like we had here, apt-get update, which can take a while, apt-get install Postgres can also take a while. So in this case, when I'm doing development, it's actually better to have a bunch of layers, because then when I do my own, say, personal stuff that start up my web application or whatever, then only the changes that I do will have to be rebuilt. So I don't have to reinstall Postgres every time I do the build, because it caches it. Here's an example of a real Docker file. This is the Nginx team. And as you can see here, they they set up what version of the Nginx it is. They install some keys, because they want to be able to install it from their own repository. And you see they group the apt-get update and the apt-get install here to flatten it out. They create a couple of symlinks to the access log, and that's because they usually you want the logging to be written to standard out from a Docker container, because then you can take advantage of Docker's built-in logging and log drivers, etc. They also add a volume here called var cache nginx, because that's one part of nginx that you usually want to reuse if you start up a new container. And then finally, they expose 2 ports, 80 and 443. And then finally, they run the command nginx and tells it to run it as daemon off. And the reason for doing this is that if the process is not running in the foreground, the Docker daemon will consider your process dead. So either you do it like this, or you have a nginx config file where you tell it to run not as a daemon. So a Docker file contains a bunch of directives. They can be used in both runtime, at build time, or just runtime. And the build directives are, that tells you what file it is, or what image you want to base your Docker file on. Maintainer is just metadata information with contact information. Copy and add is similar. Add is like copy with some extra bells and whistles, like unpacking tar files and handling URLs. And then run will just run an arbitrary command. On build is used if you want to inherit from other images. And it's very nice because many environments, like the Java community creates like a Java 8 image, and they will create a Java 8 on build image. And when you use an on build image, if you just follow the standard conventions, you don't have to do anything else. You just have to write one line in it from Java 8 on build, and then everything else will just work, and it will create your image based on the JDK or the Java image. Docker ignore works like git ignore, but it tells you not to include the files in the build. It's usually for if you say you have database stuff that you don't want to include, or a lot of big files that you don't want to include into the image. Just to speed up building, basically. Working directory sets the working directory. User sets the user that will be running the commands from that point on. And also, in runtime, it will say what user it will be that is actually running inside the container. And environment is used for setting environment variables. Then the last 4 here in the run column is the command is the actual command that is run when you run the container. I'll skip over entry point because it's, you can look into that yourself. I'll skip it. Exposes the ports that you want to make open up. But it doesn't actually open up the ports when you run them, because you have to tell the run command to open the ports. I'll show you that later too. And volume finally tells you that this directory inside the container will not be handled by Docker. It will be handled by the host system. Okay, so containers. Containers are just running instances of images. Or they don't have to be running. You can stop them, pause them. Anything you can do with a process, you can do with a container. So the containers run, like I told you before, in the top layer of the image hierarchy. And an image can be a writable container, or you can tell it when you start up that it's a read-only container. But if you start it as a read-only container and your process that you're starting up tries to write to the file system, it will crash. But it's really good if you don't really want your container to run or write anything inside the container, then you should start it up as a read-only. And most of the time you should start it as a read-only, because most of the time you want to take care of the files that are written. And you can just mount a volume as temp or as cache or logs or whatever it is that you want to save for later. There are a bunch of commands for interacting with containers. I'll let you see them for a while, and then I'll go into the most important ones. So the main command for running a container is docker run. And if you want to run it as an interactive process, you usually give it the options IT. And if you don't care about the container being around after it has stopped, you can also give it --rm, which will just tell Docker to remove it when it stops. So here I start up an Ubuntu image, and this will run the default command from the Ubuntu file, which is a bash shell. So I will have a bash shell inside an Ubuntu container with this command. And there I can do anything. I can install stuff and try out different versions of different services, whatever. And then when I exit, bam, everything is just gone. So it's really nice for trying out different things. If I don't want the process to just die when I stop or when it stops, I can run it in detached mode. This is like running it in the background. And I can also give it a name. So here in this case I start up, it's not a good example because the bash shell will actually not do anything when it's just run in the background. So a better example is running a MySQL image. So here I start MySQL image. I'll give it a couple of environment variables, and these are often defined they're always defined in the Docker file, but they're often defined in the README where the image is created. So here I give it a user, MySQL password, and then I also give it a bunch of other environment files, which are, environment variables, which are read from an environment file. If I want to publish a port from inside the container, so here I run an Nginx server, and I want to publish it on port 8080 on the host machine. So the port inside the container is 80, and the port outside on the host is port 8080. Then I can access this if I'm on say on localhost 8080, if I'm running on an Nginx or a Unix system or a Linux system. If I'm running on an OS X system, I will have to access the IP address of the virtual box instead. I could also give an interface to the P command. So I can tell it I only want it to be available on the localhost or 127.0.0.1 address. Because in the previous case, it would run on all network interfaces, which would make it available from the internet if my computer is accessible from the internet. And as you can see here, the Nginx file exposes both port 80 and 443, but 443 will not be available outside. It will be available inside the container, but it will not be available outside the host. But if I, on the other hand, start it up with a capital P, which means publish all, it will publish all the ports that are exposed inside the Docker file. But since it doesn't know if there's already something running on the local host, it will publish them on random ports. So you have to check out you do docker ps or something like that to check out what ports they actually got on the host. If we run something with docker run link, then we can get access to another container from one container. So here I start up a Postgres database, and I call it DB. Then I do docker run link db db, which means that inside my application here, my app, I will have access to the host name DB. So I can access the Postgres database on port, what is it, 6345 or something like that? I don't really remember. That's the default port for Postgres. And this is really nice, because then I can start up a bunch of different services on my machine, and then I just link them together, and I get access to them through my chosen name. I could also set limits when I run things. So if I use -m, I can limit the memory that this process gets, and if it reaches that memory limit, it will just crash. But you could also have a strategy for how you restart the application. So if you set a limit and you have a restart strategy of always, it will crash the application or the container and then just restart it again. You can also limit CPU shares, but shares is kind of like the nice command in Linux, where you have 124 shares to split up. So if I tell this my app here to have 512 out of the 1024, it doesn't mean that it will get half the CPU. Because if I start up two other processes without limiting their CPU shares, they will get 1024 each. So that means that my process will only have a fifth of all the available CPU shares. And then finally, you can run with set a user. And this user can also be set with the user directive inside the Docker file. So if you have a running container and you want to get inside it because you want to debug something, or you just want to look at the files if they have changed, or even change files, you can do that with docker exec. And docker exec, you usually give it -it again, because you want an interactive shell and you want it to support signals, which is what the TTY option means. And here I get inside a running container with a hash named SF2C42, and I get just a normal shell there. And then I can inspect what's going on inside this container. I could also use docker cp to copy files. It's similar to how secure copy works. You can copy files into the container and out from the container to inspect it. So, volumes. Volumes provide persistent storage outside the container. So, it works something like this. The volumes are attached to the top layer of the running container, and they are created with docker run-v. So, if I do docker run-v var log, it will, inside the Docker container, the directory var log will be mounted on the host. And in this case, since I'm not giving it a place to where I want it to be mounted on the host, it will just be mounted under, by default. You can always configure this. But var log, var lib docker volumes, and then the name of, or the hash of the running container, and that's where var log will be. But many times you want to know where your files are, so you could just tell it, okay, I want the log files from inside the container to be written to the temp directory on my host machine. And then the host file system, it will be mounted in the temp directory. You can also, since I think it's like Docker 1.8 or something like that, you can actually interact with volumes via a command, docker volume. So you can list all the volumes, docker volume ls. You can create the volume with docker volume create. And you can remove and inspect them too. So if I create a named volume like this, docker volume create, name my volume, then I can use, instead of a path, I can use my volume. And this will be mounted on the host file system under var-lib docker volumes, my volume. And there's also other things that you can use with volumes there, because they have added a while ago drivers. So you can have a volume driver that actually mounts it on an EBS, like the Amazon Elastic Block Storage or block storage. So it's getting a lot better and more mature. Docker Hub. So Docker Hub is the official Docker registry. And since a little while, or actually quite a while, it supports something called official repositories. And that was really nice. But before the official repositories were there were like 100 or 1,000 different Nginx images. So you didn't know which one you were supposed to use. But now the Nginx developers are actually managing their own container, and since they are the developers of Nginx, they have been able to publish this on the top level of Docker. So instead of having your own namespace, which you have normally, they are so you just do docker run nginx, as you saw in the examples. And this is the way it is with a lot of different kind of images, like Ruby, Node, Java. Unfortunately, I think it's still the Java images are using the OpenJDK because of Oracle's licensing issues. But like George said in the talk this morning, it sounded like they will provide official, say, Oracle JDKs or JREs. But I don't know about that yet. Another thing is that you can have as many public repositories as you want under your own name. You just register and then you can upload your images. But since they're public, anyone can pull them down. But you could also have private images. And you're allowed to have one private image for free. And then there's a payment plan, depending on how many images you want to keep. They also support automatic builds, which is really nice. So if you have your code for your images or your Docker files stored on GitHub or Bitbucket, you can just link them together with Docker Hub. So every time you push to GitHub, it will be automatically built and published on Docker Hub. Nice. To interact, you use Docker pull or Docker push. And if you don't have an official repository, you will have to push it under your name. There are alternatives to using Docker Hub. You can use your own hosted Docker registry. The code for it is provided by Docker. So you can just pull it down, and it's actually running as a container. So you can just run a container on a dedicated machine, which will contain all your images. And that will not be accessible to anyone but you, unless you want to. Amazon also started with a container registry. It's currently not available in EU, just in, I think, in US East, but I'm not. But it will come in a while. It just takes a while for it to get here. And Google also supports their own registry for free, I believe. So when you have running images or running containers, and you want to find out more about them, or you want to find out more about images before you run them, you can inspect them. And there are a bunch of commands for this too. I'll just let you see these like an overview, and then I'll get into details again. So Docker PS is similar to the normal PS command. And in this case, when I do it --all, it will show me all the containers, both running and stopped or paused. Docker inspect will give me a large file containing all information, all metadata information about the running container. What ports are exposed, what environments are available, what volumes are mounted. Everything you need to know you can find by doing Docker inspect on your image or your container. Some tips and tricks. To get the ID of the last container, you can do Docker ps-l for last and -q for being quiet. Just give me the ID. And this is really useful if you want to do scripting to find out and do something with a container. If you want to find out the IP of a container, you can do Docker inspect, but it also supports format directives, which is what's it called? Go templating language. And in this case, you just do network settings, IP address, and you will get the IP address of the container. To find out the environments variables of a running container, you just do Docker exec, the name of the container or the ID of the container, and then you just run the command env, and it will give you a listing of the environment variables. To get a faster development cycle, so you don't have to rebuild the image every time you want to, when you make changes, you can use volumes, and I'll show you how that works. In this case, I have a working directory which is called serve app, and when I build this Docker image, I copy all my files from my local directory into that. And then I Docker build it with a -t, I'll call it my app, and the current directory. And or if I just want to run it without, well, with it going away, I can do it --rm when I run it later then. But then the latest part here is where I mount my current working directory under server app. And this is really good, especially if you're doing web development, where you just keep on changing files and then you want to see if the CSS has changed. If I wouldn't have mounted the directory like this, I would have to run these two commands over and over again. I have to rebuild my application, and then I have to run it again. So stop it, build it, run it all the time. But by mounting the files, the current file directory, into the container, I can just do changes in my file system and they will appear inside the container. Docker Compose. Docker Compose solves it's for running many containers together, because the Docker commands normally are just meant for starting up one container. But if you want to run a few containers that are linked together and you want to always do that, you can use Docker Compose. And Docker Compose lets you write directives like this. This is not exactly the same as the options that you give the run commands and build commands, but very similar. So in this case, I do Docker, I'll show you later. But I have two containers here. I have a web container, which is my own, which I want to build. And I have a command, which I want to run when I run that container, which is python app.py. I expose the ports, and I add a volume, and I add a link to the Redis container. And then I also have another container, a Redis container, and all I have to do there is just give it image Redis. And when I do Docker Compose up, it will pull the Redis container, it will build my web image, and then it will start both of them. And as you can see, in this case, the log just started coming out from both these containers. If I do docker compose ps, I can find out information. Yeah, 2 minutes. And it will just list the processes that are handled by my docker compose file. If I do docker ps, I will see all processes that Docker is handling. I can do other stuff also with docker compose. I can run a single container just to run a command there. I can scale it, so I can start up a bunch of containers. I can start 2 web containers and 2 Redis containers. And I can just list the logs. Security. There are a few security problems with Docker. Images are currently not properly verified. It's verified, but it's not guaranteed to be correct. It will improve, and has improved already. And if you get root in a container, it is possible for you to get root on the host. So it's not safe to run multiple containers from different companies in the same Docker host. And remedies for this is to use trusted images. Don't run containers as root, because then you cannot get access to the host. And if you allow a container to be run as root, then you should treat it as root outside the container. So, summary. Docker fixes dependency hell. It allows you to write or to use a production-like environment on your local machine. It's really fast, and if you need to run multiple containers, you should use Docker Compose. And if you want to read about this, there's a blog that I've written that contains basically this information. And that's it. Any questions? I think we have a microphone.
I have 2 questions.
Yeah.
The first is Docker available for embedded systems like Raspberry Pi or other smaller systems?
No, I don't know, actually.
Okay.
Maybe it is, but I don't know.
And the second question is, are you able from a Docker image to access hardware like Bluetooth dongles or other things that are connected to the virtual machine?
Yes, you can mount stuff as volumes. So if it's available as a driver on the host machine, you can mount that directory or mount point or whatever you need to access, the device driver on the, yes. So
okay, thank you.
Yep. Anything else? Okay, thank you very much.